Hello and welcome to another Carbon tutorial. This time I want to talk about the Carbon Mesh Deformer node. This is a custom node which is cross-platform, so you can have it available in the Maya plugins and in the Houdini plugins and also in the libraries. Our Carbon Mesh Deformer is similar to the Maya proximity wrap, or in Houdini the combination of cloth capture and cloth deform. But there are several models you can use from the Carbon Mesh Deformer to decide how you want your mesh to be deformed. So let's dive straight into it. You can find the Carbon Mesh Deformer straight here on the Carbon shelf, or if you go to the menu under Carbon, Create Utils, and then Mesh Deformer. So first thing, I'm going to just show you what the scene is. It's a simple grid falling over a sphere. Here we are. All right, now let's go to the Mesh Deformer. And we have three major inputs. We have the driver. The driver is the mesh that is not deforming, but it is doing the deforming. And geometry is the mesh that is being deformed by the driver. Furthermore, we have a driver reference, which is used for initialization of the mappings. For the driver, you can also specify a phase group, so a subgroup of the driver mesh that affects the geometry. And for the geometry, you can specify a point group, so a subset of the whole points of the geometry, which will be deformed by the driver or the subset of the driver. Per default, these are set to all, shown by the asterisks in these fields. Next up, you can also save the mapping to file or load mappings from file. Especially when you're using pretty high resolution meshes, it can take several seconds to create a new mapping, and you want to ensure that you're constantly using the same mapping even when reloading the scene or loading up the scene in a new version of Maya or Houdini. And you can share them obviously between Maya and Houdini as well. So when your mapping is supposed to be consistent or it takes too long to recreate it every time, you can just save it and import it again from file. The final section is for new mappings. You choose your deformer type and then press Update Mapping to create the mapping. There are three deformer types: skinning, analytical, and smoothing. We have detailed written documentation about the three deformer types. You can find this in the documentation distributed with your plugin. Simply open the documentation, go to the reference section, and then open the Carbon Mesh Deformer page. When you scroll down to the section for the deformer types, you can find all of this listed. I will also quickly display this on the screen, and you're welcome to pause the screen and read through it now. The skinning deformer is the most stable and default deformer. This relies on the four closest triangles of the driver mesh for each point of the geometry. It's fully procedural, does not rely on any user radius or scale. So just go to it, update mapping, and nothing else you have to worry about. The analytical deformer, the second option, it generates an infinitely smooth result without departing from the collision cage of the driver mesh. It relies on an analytical equation for the positions instead of a convolution or a blend. It's also fully procedural and does not need any user radius or scale. And then the third one, smoothing. The smoothing deformer relies on a brute force smoothing kernel to combine the motion of multiple driver primitives to update each point of the geometry. This is a more flexible version of the skinning deformer, where you can have your geometry points mapped to more than 4 driver primitives. It all depends on the radius. While this tackles the skinning deformer's weakness, which is smoothness, it compromises its strengths, so it uses more memory and it does not necessarily preserve the driver's silhouette, all depending on how you set your radius. You can set the radius manually and then press Update Mapping, or you can use the estimated radius, which has a look at the driver geometry and then makes an estimated guess of what a good radius would be. You should use this as a starting point, and then you can go larger or smaller depending on whether you want to have a smoother result or match the driver more closely. So let's get started. For the driver, we will select the output of the cloth simulation, which is p-plane cloth 1 output. And the geometry, I've created plane 2 here, which is a high resolution geometry. Let me just quickly hide the simulation. We have the high resolution geometry here, which is 100 by 100 grid. And then we have the cloth output for the driver, which is 40 by 40. All right, so if we want to use a high resolution, we should choose for the geometry, which is P plane shape 2. There we go, it automatically created an output from our mesh deformer. And let's start back up with skinning. Update mapping, and here we go. It shows you the information of the driver mesh in terms of triangles and points, and the points of your geometry to be deformed. And it also shows you how much time it took to update the mapping, 14 milliseconds, so basically an instant. Now, if I press play, you're going to see the high resolution mesh being deformed nicely and moving along. I can overlay the output of the cloth You can see here, and maybe let's put a different color on it. I think I already have a material here. There you go. We have blue material on our simulation output, and we have a gray material on our high resolution deformed geometry. This is matching pretty well using the skinning deformer. All right, now let's have a look at the analytical deformer. And what's wrong? Well, what happened? This is pretty easy. We did not specify a driver reference. So what happens when I press update mapping on frame 150 is that it tries to create a mapping between P-plane shape 2, which is up here, and our driver, because there's no driver reference, it's using the driver. And our driver currently is down here, this blue mesh. So it creates a mapping between a grid up here and the mesh here. And then obviously that's going to be very convoluted and gives you a not very good result. And the analytical deformer works very strongly when you have points outside the geometry's region. So even if we go to the skinning deformer, it's not going to look very great. It might look great on this frame, but let me scrub. And yeah, that's not good at all, is it? So what do we need to do? Either we need to go back to the first frame, press update mapping here, and we can do this for this, we can do this for this analytical deformer as well. Update mapping and all is good now. Or instead of going to the first frame, what we can do is we provide a driver reference. So that way we can update at any point, because a driver's reference is a static mesh, and this we need to set to the start mesh of our cloth, which is static, it doesn't move. So let's choose P-plane shape 1. And now we can press update mapping and all is good. It's the same as on the first frame because obviously that's equal. All right, and the other output is this moving deformer. Let's press estimate radius and update mapping. So we can see it is much smoother, and just quickly compare to skinning. And skinning deformer, and I'm just gonna hide quickly the output of the cloth. You can see in the skinning deformer we have a tight mapping, but it shows through the lower resolution geometry from our input mesh, from our driver. Now, if I swap to the smoothing deformer now, you see it's slightly grown, so it's less close to the driver. And if I show the driver again here, we definitely see there's a slight discrepancy now, but we get a very smooth behavior. So when you use the smoothing deformer, it's all about finding a balance between having a radius that is big enough to not show the underlying low resolution mesh structure, but not too big where it's way off and we get a mesh that does not even capture silhouette. For example, if I triple or quadruple this to 0.2, update mapping, now look at this. This does not look at all like it's capturing our mesh from the driver, from the simulation. So this is way too big, and we want to reduce it. Again, estimate radius gave us a pretty good result, but maybe we want a bit closer, so let's reduce slightly more. And there we go. And as we're going closer and closer to a smaller number, we're going to get something that matches closer, but we're going to get this geometry showing through again. So let's go up again. 0.3 was probably a sweet spot where it was just disappearing, but we still have pretty good match of our mesh. Now, one interesting thing I want to show you about the analytical mesh deformer. So let me just hide the input mesh here. And I'm going to go up to our cloth. And I'm going to reduce the geometry of our simulation cloth from 40 to 4. I know this is quite crazy, but follow me along with this, please. All right, so now we need to update the mapping. All right, here we go. Now we are on the smoothing deformer. And we might want to estimate the radius again. Here we go. So what happens with the smoothing deformer is that it tries to smooth it out, but we are not guaranteed that we're actually matching our input driver at any of the points, similar to the skinning deformer. Let me update this. And while there's a closer matching of the overall silhouette, you're not guaranteed that the endpoints, for example, here will match between your high resolution mesh, so your geometry, and your low resolution mesh, your driver. But that's where the analytical deformer shines. The analytical deformer makes sure that your geometry goes through all of the points for all of the geometry cage of our driver. So if it is very important to you that you match these endpoints, for example, you should go with the analytical deformer. If it's not so important, you choose skinning if you don't want to think about it and you want a pretty close mapping and you're happy with kind of showing some of the underlying structure, or you go smoothing if you want a little bit of a smoother behavior. And here we go, but it might not match it and you have to manually slightly tweak probably the radius parameter. This is still too big. Let's reduce it. There we go. Now it's probably too small. It's more like the skinning deformer again. But this is just a theoretical example because obviously you wouldn't simulate a mesh with such low resolution. Now here I have another example. Here I have two cloths falling over a sphere. It's very similar, but both have a decent amount of resolution. Also, our deformers here are set to analytical right now, but let me set them to skinning. And obviously you need to press update mapping for it to update. There we go. We see the lower resolution texture coming through, but that's not the point I'm trying to make. The point I'm trying to make is we need to make sure that our render mesh, that our geometry is about the same thickness as our virtual thickness of the cloth. So what do I mean by this? Well, here what we have is cubes instead of thin planes for our geometry. Not sure if you can see, but it got some thickness to it. You want to make sure that this thickness does not exceed and roughly matches the thickness of your cloth. And the thickness here is 0.001, so it's 1 millimeter, and it's the same on the cube. Now what happens if it doesn't match? So first case, our cloth is way thicker than our render mesh, our geometry. So I'm gonna change this from 1 millimeter to 2 centimeters, so make it 20 times as thick. Reset the simulation, and if I show the simulation, we see very thick cloths now. You run these, what happens? Well, obviously they drape differently, and while they touch here in the simulation, because our render meshes are much thinner, what happens is they float on top of each other. You get quite a gap, and visually this can be quite disturbing, because why would they float on each other and not collide correctly? So this is the first case where your cloth thickness is way thicker than the thickness of your render meshes, of your geometry that you are deforming. Now let's look at the second case. I'm going to revert the cloth thickness again to 1 millimeter. But this time now we're updating the cube thickness, and I'm just going to make this 20 times thicker. I'll set this one to 2, and this one also set it to 2. All right, so what do we have to do? We have to update, reset the simulation, and we have to update the mapping as well. Now, here we have our render meshes, and if I hide them, you can see here's our simulation. This is thick now. Sorry, this is thin now. So running the simulation again, this is a result you would expect. You get thin meshes, and they're quite nicely aligning here. There's no overlaps. It looks very believable. Now, what happens when I show the render meshes now? Because my cubes are so thick, what you get is actually overlaps. And I've colored one in turquoise and one in gray, so you can very much see now that they basically completely overlap here. That's because the cloth meshes are thin and the render meshes are so thick. And this obviously is very wrong when you get this visually overlapping. And it's something to take very great care of when you're setting up multiple layers, that your render mesh, so your geometry, if it's thick, is about the same thickness as your cloth thickness. Another thing to try to keep in mind is that you want to make sure your deformer types are roughly the same. Let me show you an example. And first, I'm going to revert the parameters to something sensible. All right, so now we have sensible results where we have simulation meshes and our render meshes, our geometry that we are deforming, have the same thickness, and we get some good results. Because it's very thin and our input meshes are very low resolution compared to our deform meshes, we get some small overlaps. But it's very important that we take into account that our deformer should also be the same thing to reduce the amount of overlaps. So if I have one deformer set to skinning and the other deformer I now change to analytical, update the mapping, we should expect more overlaps. While if I again go to the first one then and update mapping, we should go back to less overlaps. Similar thing if you go, for example, to smoothing. Go estimate radius, update mapping, and we can see now that there's quite a lot of overlap between those two meshes because it's just a geometric process. There is no collision correctness in here. If I go to the second one, smoothing, estimate radius, update mapping, and we're much better again because we applied the same deformers. If one of them obviously had a much larger radius, Now it wouldn't match again anymore. 0.2, update mapping, and it's off again. So just one thing to keep in mind, if you deform multiple geometries, you might want to make sure your deformers are synced as well, so you get very similar kind of deformation behavior and you reduce the number of overlaps. So in summary, you want to make sure that number one, your geometry, if it's thick, has the same thickness as your cloth. Number two, you want to make sure that your deformer types are the same between two meshes to minimize the amount of overlaps you get. And number three, if you want to minimize overlaps while preserving the same shape, you should try to make sure that your simulation meshes and your render meshes, so your drivers and your geometry, are not too different in terms of resolution, because otherwise the high-res mesh is just trying to capture the low-res and you're going to get artifacts and more overlaps. Now let's look at a couple more scenarios that are more aligned with what you might encounter during production. Here we have an avatar wearing a t-shirt and wearing pants. Let me just simulate this. And the avatar starts walking. I'm going to focus on the pants for this scenario. The t-shirt is just to complete the outfit. So these pants, and I'm visualizing, by the way, the output of the simulation. So I'm not visualizing the simulation physics, but the actual output mesh. This is simulated as one welded mesh. So it's one cloth and it is not made from panels, just a single cloth. Now I can do various ways to now put a thick render mesh on this. The first approach is, well, why don't I just put also a welded render mesh, but just make it high resolution and thick. And I have prepared one of these right here. And it's just a single mesh and it's thick and it's high resolution. Let me hide the start mesh and we see this is much higher resolution. Okay, let's create a mesh deformer. Mesh deformer here. Let's go all the way down. This is alphabetically sorted. We're looking at pants welded start. And here are the two meshes, pants welded start mesh shape and cloth output. So the driver is the output of the simulation. The driver reference is our pants start shape. And our geometry is our pants 3D render mesh shape. There we go. And now we have our mesh deformer output here. All right, when I run the simulation, we get behavior, but what do we see? We see some issues here. Well, how come? Now, the problem is that when you try to do a mapping in 3D, you can have geometries that are pretty close to each other. So this could be here on the bottom and the hems of your trousers, or sometimes if you have long sleeve shirts and the arms are closer to the body, this can happen there too, or in the armpits. Now the problem is that when you create a mapping, it is purely by proximity. So if I look at the mesh deformer, the skinning uses the four closest triangles, and the four closest triangles might unfortunately be one that are not part of the same pant leg. So when we step forward here, let me zoom out, we get part of these points being mapped to the simulation mesh of the pant leg that's on the other one. And it doesn't matter now if I change our deformer mapping, it will not really fix the problem. It will probably just make it worse with just moving the deformer. I can try to make it very small, and now it's too small. We don't have anything in range. Let's see if you can bigger, and no, we get artifacts. So the skinning deformer is probably the most stable one, and it's generally the most stable one. If this already fails, then you know you got a problem. Well, how can we deal with this now? Because we have a welded simulation mesh, we really can't change something in our simulation mesh, but what can we do with the render mesh? Well, let's have a look at the simulation mesh. It is welded. And where is it? Here, pants welded start mesh. Well, if we have set up our UVs correctly, we can use the UV to panels node, which is here, UV to points node, to create our flat panels as they were originally in Glow. And the uniform scale, if correctly exported, is 100. And here we have our flat panels of our pants. And now we can use a flat render mesh. So let me hide this one. And I actually have render pants 2D, which are here already. There we go. Now they are slightly offset because the way Glow exports, it always puts a 20 on the Z axis. So I just do -20 and now they overlap. So as you can see, this was exported as 5 separate meshes. I'm just going to combine them to do this now. And we do combine. I'm going to create a duplicate to hide the history. And there we go. Pull render mesh panels, and this is just pants single mesh. Rename it. So we have a single mesh now for our render and we have a single mesh for our reference, and we can now apply this. I can already select this mesh and then hold Control, go on the deformer, and change the driver reference now to our flat panels, which is the second one in our drop-down after none. There we go. And what do we want for the output? We want this geometry and this one. Need to update the mapping. There we go. And now we have here our new render meshes. And let's see what this looks like after. Let's hide these ones. And what else do we want to hide? We want to hide this one and this one. And there we go. All we see now is the Deformer output. And if we run this now, we can see because we created a mapping in the flat space, there are no issues with the geometry being assigned to the wrong panel because there was plenty of space between the panels if you look here. So as long as you don't set your radius so large that, for example, this point gets mapped to here, you're all good. Let's explain something else. So keep in mind that now our render panels, our render geometry here is separate panels, which means the output is also separate panels, separate meshes. So for example, if you right click, click vertex and double click somewhere, you can see that it selects everything connected, which is part of that panel. Let's go back to object mode. There we go. Now, with the skinning deformer, we cannot see the edges much because it's all a very nice tight deform. Similarly, when I go to the analytical deformer type, and let me change now, it also deforms pretty nicely. But now you can get some slight issues once you go to the smoothing deformer. Let me estimate the radius, update mapping. Now, once you estimate the radius, and usually you get a smoother result than with the skinning. And it smooths out all the points, and you will end up seeing seams coming apart because now the point on the edge is deformed by a much larger radius, so we'll start pulling away from the edge. So if I even further increase the radius, you can see this much stronger. There you go. We have a much smoother result of the pants, and ignore that they're now overlapping with the shirt. What I want to talk about is now we got an opening on these gaps here. So how can we deal with this? One way you can deal with this is to actually create a detail and range setup on your radius. So what you can do is you can set a smaller radius on the edges and a larger radius on the range. So let me show you how this can be done. We need to hide our output and show the input of our deformer mesh. Now in the mesh deformer, we can go to detail, and it's already setting an attribute here. We just press the button to paint our detail. There we go. And it's bringing up the painting. And we need to paint on our mesh here. So here we got a nice view. What I want to do first here is actually put a small value, put 0 on the edges, and put a large value on the center. So let's flood everything with a value of 1. And now swap to painting 0. And I'm going to go over the edges to basically reduce the value on the edges. All right, I'm done painting. Obviously, since we have 3D meshes, make sure to paint both sides and the edges as well. Now we can hide the paint tool, hide the input mesh, and show the output mesh and go back to the mesh deformer. All right, here we had our large gaps on the trousers. Let's see if we can improve this. All right, so we change our base to something small. Let's go ahead, estimate radius, and I think we want it a bit smaller to make sure that those gaps are being closed. All right, there we go. And this looks pretty good. All of the gaps on the edges have now closed nicely. Let's look around here. Yeah, all the gaps are closed. And now we can bring back some of the smoothness everywhere else. Now we go to the range, and we can now tweak the range to give a little bit more leeway. So let's just maybe double it. So add a 1 to the range as well. Press update mapping. And we get a little bit more smoothness showing through. So you can obviously try to increase the range. So if you go too large on the range, for example, go to 5, you're going to start seeing issues basically where the paint map stops and where points are going to be more or less affected. And then you're going to get the 2 layers because we have a thick mesh starting to mess with each other. So I wouldn't go too much. I would maybe go 1. And there we get pretty good results. We get more smoothness on the rest, but we still have our seams closed. Obviously, if your render mesh is thicker than it is in here, then you can use a larger radius and you have less problems. Also, you can minimize the effect by smoothing your paint map or drawing more accurately than I have. Since we have flat panels here and we have a 3D welded mesh, actually our simulation mesh has less points in here than it has in here, because obviously everything that was welded here on the edges in our simulation mesh in the flat panels now is 2 points, so one here and one here, which were welded together. This is fine for the mesh deformer because the thing that matters is that your driver mesh surface triangles are the same as the driver reference surface triangles. So they need to be the same order and the same number, but obviously the points can be slightly different as long as if it's all cohesive. This is the same as when you use the welded panels cloth model. And in fact, we have everything basically ready for the welded panels cloth model. So we could go to our pans, we could change it from standard to welded panels, and then we provide our reference mesh, which is here our flattened mesh. And then we can do this as well, set simulation, and then we can just use this model as well if we want to. And we're using our flat reference panel to apply the metrics to our simulation. And just to finish up this video, here's a quick example that's already set up using the garment processor Glow Unwelded. The garment processors do all of the heavy lifting. When you input your flat panels render meshes and then your 3D start mesh, everything is done under the hood, given that you set up correctly your UVs in Glow and you're passing the metadata. I'm at the final stage 6, where the deformers were already applied, and we can see a section here called Deformer Geometry, where we have not only the meshes with a deformer, but also second stage including detail. Details are all things that you want to deform additionally on top of your main panels. So in this one, let me zoom in. The details are, for example, these stitches. But details could be other things like little labels or other objects like small zippers or little buttons that do not necessarily need to be simulated as separate rigid bodies. What happens is we have our main panel being deformed by the simulation output, and then based on the main panels, so the deformed output, we're deforming our details. This is a nice way to layer it up. So you have your panels, make sure they're looking fine first, and then based on the panels, you're deforming your details, and you have additional deformers in here. You have for each of these details, you have one additional deformer. On the carbon garment processor, there was a previous stage called merge details, where you would have been able to actually merge all of these details here that were assigned to the same panel into a single mesh. And then instead of having these 4 extra deformers for the details, you would only have 1. Since there are quite a lot of deformers now in this garment processor, there is a macro here on the garment processor itself where you can update all of the mapping in one go by pressing Update Mapping. You probably saw there was a pop-up video going through all of the mappings. Now click it again, 3, 2, 1, go. And this updated all the mappings. Obviously, if I change this to analytical, for example, we should see a slightly different result. There you go, and it's slightly changed. Or if you go to smoothing, estimate radius, this will estimate the radius for all of the deformers individually, and then press update mapping, and it has now deformed based on the smoothing deformer. I hope this makes sense and gave you a deeper understanding of what the mesh deformers do and what are the pitfalls and what are the advantages of each deformer. Thank you for watching and have a good day.